So welcome you all to another lecture session on this course on line commutated and PWM rectifiers, and we are going to talk about some basic ideas about voltage source converters. So if you see the course content and the course structure, we are basically now moving into this third topic here, and we are going to talk about the AC to DC converters with this inverters, or we also call this as inverters or PWM rectifiers. This term of PWM rectifier is more popular, but it is basically a voltage source converter. Okay, so we'll talk about this in details, and we will talk about today about the understanding of sinusoidal PWM and some of the steady state analysis, and subsequently in the subsequent lectures we will be moving into the steady state phasor diagrams, leading lagging operation, bidirectional power flow, and then also some little bit of hysteresis control. So these things we will cover as part of the third week of course. So yeah, so this is the total content of what we will be covering today. So three-phase voltage source converter is a popular choice of converter for grid connected or motor drive applications. So you can see here this converter is already, I am expecting that you already know about this converter. Basically you can see here there is a DC source here and there is an AC load, okay, here, or it can be an AC grid or AC source also, okay, at this side, right? So if there is an AC grid, then we actually have this phase A, phase B, phase C. This is the grid, okay, and this impedance here will be a filter. Okay, if the grid is not there, this whole thing, this can also be a motor load. Okay, so this can be a motor load. So basically if you understand, therefore it is that a voltage source converter can act as a DC to AC converter. So this voltage source converter here, this is a DC, and here on this side we can say that this side here it is producing AC, right? So therefore when it is usually converting from the energy is flowing from DC to AC, we call it as inverter, and when the energy is flowing from AC to DC, we call it as a rectifier. So you can understand that the energy can actually flow in this converter from the AC grid, for example, to the DC link, or during regenerative mode of a machine, okay, the energy can flow from the AC side to the DC side. Okay, so a voltage source converter can act like both as an inverter and a rectifier. Okay, and therefore it is correct to use the word converter for such a power circuit. Okay, that is why we have used the word converter. Okay, we could have also said that this is a inverter, we could have said this one, or sometimes we use, instead of this word, we say that this is PWM rectifier. Okay, it's the same thing. It's basically a voltage source converter, but depending on the way the energy is flowing, we can say whether it is working as an inverter or working as a rectifier. So in this lecture we will not use it specifically as an inverter or a rectifier, and rather we will say the word converter. Okay, the voltage source converter. So VSC, this is the term that we will be using, keeping in mind that it can both act as an inverter or it can act as a rectifier. Okay, so with this understanding, we look into the circuit of this converter and we find that we have three sets of half bridges working together in this converter. So it consists of three half bridges. Okay, and as I told you, the energy can flow from AC to DC side or vice versa. So this is a bidirectional converter, and just now I explained that this voltage source converter can act like an inverter or it can act as a PWM rectifier. Okay, so if you want to really understand or go in depth of this understanding of this converter, we have to understand how a half bridge works. Okay, this is a very quick recap of what I want to do. So this is a half bridge circuit which you can see here. This side is the DC side and this side is the AC side. Okay, so in many of the applications, this current which is flowing, this current is AC. Okay, this current is sinusoidal AC in many of the or most of the application. For example, this AC side can be a motor load. So for example, this half bridge is a phase. Okay, A phase of the system, and so this is carrying the A phase motor load current or A phase grid current. Okay, so so the current here can be sinusoidal. Okay, and yeah, it is AC in nature. It has both positive and negative sides, or positive or negative halves, right? So here there are two switches, and you can see that if I turn on this switch S1, okay, I get a VD voltage, and if I turn on S2 switch, I get a 0 voltage. This VAO we are talking about, this VAO is also called as the pole voltage. Okay, this is also called the pole voltage. So depending on the direction of the current, either S1 or D1 will conduct when we get VD voltage, and when we get 0 voltage, either S2 or D2 will conduct depending on the direction of the current. So let us see one example here. For example, now here I have replaced the load with a current source, AC current source, and this is the load current waveform. You can see here, this is the load current waveform, and I have given the pulses to S1 and S2. You can see here the pulses are given to these two IGBTs. Now let us consider this time interval T1. In this time interval, okay, the IGBT switch S2 is given pulses. You can see here S2 is given pulses, but the current is positive, right? So the current, the load current is like this, which is going out from the pole, from the point A, it is going rightwards. So therefore the current is positive here, and therefore even if you give the pulses to the switch S2, the diode D2 will be conducting. Okay, it will get forward biased and D2 will be conducting, and therefore VAO voltage is equal to 0, assuming that the diode is ideal. So it will flow through the D2. Okay, so even if you give pulses to S2, D2 will be conducting, right? So this is one example, but you can also see, say if you take this interval T2, okay, here I have given pulses to S1, so now the current will flow through this top IGBT, okay, like this, fine. So IGBT is switch S1 is on and VAO will be VD. So with this understanding, with this concept, we understand that all the four switches S1, S2, D1, D2 will be useful. Okay, for example, here you will find, okay, that one of the diodes or the switches are being conducting. Okay, so all these four intervals T1, T2, T3, T4, we will see that the either S1, D1, D2, S2, D2, any one of them is conducting, okay, depending on the direction of the current and the gate signal pulses given to the switches. So this is how a half bridge converter works, right? Now, once we have understood this, that okay, this is a half bridge which is working by using the pulses given to the top and bottom switches, then we can actually connect three half bridges. So here comes the A phase half bridge, and then we have the B phase half bridge and the C phase half bridge. So then we make what is called as a three phase converter. Okay, this is a three phase voltage source converter. Okay, now this output voltage here, of course this output voltage needs to be controlled, okay, because we are going to exchange energy with the grid or the load. So here comes the grid or the load here, okay. So we are going to exchange energy with the grid and load. So therefore we need to basically modulate, okay, the voltages which is available at these points. These are the pole voltages. So we have to modulate, or modulate means we have to modify, or we have to adjust the output voltage which is available in A phase, B phase and C phase pole voltages, okay. And the technique that we use to modify or adjust this voltage is basically sinusoidal pulse width modulation, okay. The reason we use sinusoidal pulse width modulation is because our grid or the motor load is AC in nature, okay. So therefore we use a sinusoidal PWM. So let us quickly recap what is pulse width modulation and what is sinusoidal pulse width modulation. Basically we use this PWM technique in power electronics to control the voltage magnitude across the load. So for example, this is the point A, okay. If we want to change the magnitude of this VAO voltage, okay, so we can actually turn on and off these two switches, S1 and S2, okay. So if we can always represent this circuit as something like a DC source here and two switches like this, and which is going to a load, okay. So we can change the voltage, VAO voltage, by turning on and off S1 and S2 switches in a complementary fashion. Of course we cannot turn on S1 and S2 simultaneously, because then we will short the DC bus, so that's forbidden. And so by turning on and off S1 and S2, we can actually control the output voltage VAO. So in order to do this, basically what we do is we compare a high frequency triangular wave with something called as a modulating wave, okay. We this is very common in power electronics. The pulse width modulation technique, or the PWM technique, is that we have a modulating waveform which is shown by the red line here, and this triangular waveform is a high frequency triangular waveform. And what we see here is that we follow a logic that if the modulating waveform is greater than the high frequency triangular wave, then the upper switch is on, okay, S1 equal to on, else S1 equal to 0, okay. So I think this is given in the next slide, okay. If the modulating waveform is more than the triangular wave, this upper switch will be on, otherwise the lower switch will be on. So which means that here the modulating waveform in this portion, the modulating waveform is more than the triangular wave, and therefore here S1 will be on, and therefore we get a VAO voltage like this, right? So this is what we get. Of course we can understand that by changing the height of the modulating waveform, I can change the width of this pulse, okay. So for example, if the modulating waveform is here, then obviously the width of the pulse will become something like bigger width of the pulse here, okay. So the pulse width becomes something like this. So therefore this becomes the VAO voltage, right? So therefore we quickly understand this statement here, that more is the width of the pulse, more is the average pole voltage in a cycle. The width of this VAO becomes higher and higher. Okay. Now, in this, one of the assumptions is that the triangular frequency should be of high frequency. The reason being that we want to make an assumption that during this period of the triangular wave, the modulating waveform does not change in its value. So if the triangular wave frequency is sufficiently high, which means the triangular wave period is very small, then we can assume that the modulating wave during that small period does not change in its value. Okay, under that assumption, actually this sinusoidal PWM works nicely. Okay, so let us assume that the height of the triangular wave is 1 and the height of the reference wave is assumed to be m. Okay, so this is m and this is 1, right? And this is 0 here. Okay, so then we can find out that what is the instantaneous duty. Okay, so this is something which you can do it quickly, that we can take this triangle here, okay, and apply the triangle rule. So we can take this triangle here and apply the triangle rule that so AB by BD is AE by EC. If you do these things, then what will happen is so this m we can put it like this, and TS by 2, so this is the TS by 2 time period and this is the T on time period, and when you go like this, you will find that the average, so MT is the T on by TS by 2 is the duty ratio. Okay, M of T we assume. Now here I have used a time, okay, for M. Because later we will see in the next slide that this duty ratio is going to vary from cycle to cycle in sinusoidal PWM. In DC-DC converter, usually at steady state, this duty ratio is constant. So therefore, in a buck converter, for example, we say that the output voltage is equal to D times the input voltage, where D is something between 0 and 1. The same principle. But in buck converter at steady state, the duty ratio becomes constant. Whereas in sinusoidal PWM, as we will see in the next slide, this duty ratio is going to vary in every cycle. Okay, so therefore this we have given M of T. Okay, it's a function of time. Okay, like this. So therefore the average voltage of VAO, okay, during this switching cycle is VAO average. We can just put it. So how much is this? This is VD into the time period. So average voltage, you can find out the total this divide the total of area of this divided by the total duration, time duration. So VD, and it is for the T on by TS, and for the rest of the time the voltage is 0. This is the rest of the time. Okay, and so if you combine them, then you can see that the average voltage is MT into VD. Okay, of course here M is going to vary from 0 to 1, right? So the VAO maximum voltage is VD and VAO minimum voltage is 0, exactly like how we see in a buck converter. Okay, now suppose we start to vary this M, okay, the M value from cycle to cycle. So here you can see how we are varying. So here the value of the MT is some value here, okay, but here the height has changed. Okay, and subsequently here in another cycle of the triangle, the value of M is going on changing, right? So if MT is going to vary from cycle to cycle, then what will happen? We have seen that the average voltage in one cycle, okay, is MT times VD. So therefore the average voltage, okay, will also go on changing from cycle to cycle. Okay, so therefore this is also called the instantaneous average voltage. Okay, VAO average here is called also the instantaneous average voltage. So if mt is varying from cycle to cycle, then the average voltage will also vary from cycle to cycle. And so therefore we can see that suppose mt varies sinusoidally. So now this is the full picture of mt. Okay, in fact what I had shown in the previous slide is a small zoomed in, so I actually zoomed this portion of the waveform and I had shown in the previous slide here. Okay, this one was the previous slide here. Okay, this is what I had taken a snapshot. So here, so this portion I had zoomed. Now if I see the whole picture now, what I find here is that mt is actually varying sinusoidally, okay, over time, and slowly over time. Then VO average will also vary sinusoidally. Okay, now what do we mean by the word slowly? Slowly means the frequency, okay, so the mt is not going to change much in a large in a triangular time period. So you can see here, actually this diagram itself also is not so accurate because usually the triangular frequency is very high. Okay, for example, typically the frequency of mt, if it is a sinusoidal PWM, the modulating waveform can be typically having a 50 Hertz component. Okay, this may be a 50 Hertz sine wave, and the triangular frequency can be easily, okay, it can be easily 5 kilohertz. Okay, so which means it is almost like 100 times more. Okay, so there will be 100 triangles in this one sine wave, within one sine wave, and in each of this small triangular period we can assume that the sine wave does not change within that small triangular period. So this 5 kilohertz is, even I will say that modern power electronics, 5 kilohertz is low, especially with silicon carbide devices coming. This value can easily go to 50 kilohertz. Very common nowadays that the sinusoidal PWM or some PWM technique or in the front end converters, this value is 50 kilohertz is very common. So which means that it is 1000 times more. So in this one period of the sine wave, we will have 1000 triangles inserted, and there we are going to compare. And so what is important here is that, so this is what is meant by slowly. Slowly means the highest frequency, okay, in that in that modulating waveform, the highest frequency is much less than the frequency of the triangle. Okay, so that is what we mean by the word slowly. It is varying over time. So now we can say that we can generate a sinusoidal output from the converter. Okay, because as I told you that m is varying over this one. So in one cycle a certain value is obtained, certain average value. In the next cycle a certain different value of average voltage. In the next cycle another average voltage. So the average voltage is going on changing, and it is changing sinusoidally with time. Okay, here you can see from the diagram it is sinusoidally changing. So therefore we can actually generate a sinusoidal output from the converter. Okay, and this can be actually mathematically expressed. Okay, and you can find out the expression of the output voltage. Okay, so this VAOT is basically m sine omega t into Vd by 2 plus Vd by 2. Okay, so we are actually substituting that mt because it is sinusoidally varying. So therefore we have substituted it here. Okay, and we get m sine omega t into Vd by 2 plus Vd by 2. Okay, we have used a Vd by 2 here as the multiplying factor because omega t is varying, sine omega t is varying from +1 to -1. Okay, so when you do this, okay, this m here, okay, this m is basically a constant. Okay, and m is usually varies from 0 to 1. Okay, and m is called the modulation index. Okay, I could have also used the word in this one, I could have used dt here. Okay, instead of mt I can use the word you use the symbol dt here because it is a duty ratio, and the duty ratio is varying, and the variation is given here as m sin omega t, right? So therefore where m becomes constant and is called the modulation index. Okay, so VAO is m sin omega t into Vd by 2. So this is the expression of the output voltage, right? So note that the instantaneous PWM value of the output voltage, okay, so the instantaneous pole voltage, so this is the instantaneous pole voltage, okay, this is the instantaneous pole voltage, and this voltage is basically varying between 0 and Vd, okay, it is instantaneous. So if you put it in an oscilloscope, this voltage is basically varying between 0 and 600 all the time, but what is inside it is this sine wave, okay, this is the average voltage, VAO average. This is embedded, okay, this is embedded inside this blue waveform. The pink waveform, which we cannot see, okay, is embedded within the blue waveform, okay. So what we will see, suppose we put it in an oscilloscope, we will only see this blue waveform, okay, this is the waveform which we will see on the oscilloscope. When I do a Fourier transform of this signal, then I find that there is a average, there is a fundamental quantity inside this voltage, okay, and that fundamental voltage is nothing but that VAO average and its expression, and that fundamental voltage is this much, m sin omega t by 2 into Vd by m sin omega t into Vd by 2. So this is the fundamental component inside this voltage, okay. Of course in this waveform you can see there is also a DC shift, okay, there is a DC shift of 300 volt in this waveform, right? So if you remove that one, so that is the fundamental component remaining, okay, m sin omega t into Vd by 2, where 0 is less than m less than 1, okay. So so therefore the fundamental output voltage, pole voltage of the converter is linearly proportional to m. You can see here that if you increase the value of m, okay, suppose you the value of m is 0.4, okay, so you will get 0.4 sin omega t into Vd by 2 as the fundamental output from the pole voltage, okay, right. So yeah, that is what I am showing here, that if m is equal to 0, okay, fundamental peak value is 0, fundamental peak value is 0. If m equal to 1, fundamental peak value is Vd by 2, because VAO fundamental is m sin omega t into Vd by 2, okay. So you can clearly see that, suppose so we can say that this is 0.4 sin omega t into Vd by 2, okay. So the fundamental voltage is 0.4 into Vd by 2, VAO fundamental magnitude, okay, 0.4 into fundamental 0.4 into Vd by 2. So of course if this 0.4 changes to 0, or this value can be up to like 1 or 0, like here we have seen that VAO fundamental peak is 0 and VAO fundamental peak is Vd by 2, okay. So that is the maximum and minimum limit between the two voltages, right? So again if this is 1, so if m equal to 1, okay, so then VAO fundamental is basically equal to Vd by 2, right? And so the RMS voltage here will be, so VAO RMS will be equal to Vd by 2 into 1 by root 2, right? So Vd by 2 root 2, which is 0.35 Vd, okay. So again I tell you, this is the fundamental component, this is the fundamental inside this PWM waveform, okay, this is the fundamental inside the PWM waveform. There is of course a DC, as you can understand, okay, there is a DC is there, DC is there, we are not talking about the DC. The DC will get cancelled in the line voltage. Okay, so we are not bothered about the DC here. So the fundamental inside the PWM waveform is the what we are interested in. Okay, and what is the magnitude of this fundamental? The magnitude, RMS magnitude of the fundamental is 0.35 VD, and the peak fundamental is, so the peak fundamental is m sine m into VD by 2. This is the peak fundamental. Okay, m into VD by 2. This we will show you in the subsequent. Okay, I'll show you sometime. Fine, I think this is clear. Then we will go ahead and we'll see what happens if m is greater than 1. Okay, usually m is between 0 and 1. So if m is greater than 1, then what happens is VAO fundamental is greater than VD by 2. So we get more output voltage. But the problem is, then at this point the sine wave, because we are doing sine PWM, as you can understand, basically the sine wave at some points are more than the triangle. So this is your triangle. Okay, so okay, let me draw it bigger way. So this is the triangle, and you have initially started with like this value. This is the, say, m equal to 0.5. okay, you started with that, and then subsequently you can go up to like m equal to 1, where m equal to 1 means you are basically touching the peak. So this is equal to m equal to 1. If you further increase, right, what will happen is at some points, right, at some points you will actually cross the triangle. Okay, so this is m greater than 1, and this here, the problem is that you are going to something called as over-modulation. Okay, and this over-modulation, you get more voltage definitely out of the, more than this what is known as sinusoidal PWM, but it will generate lower order harmonics, 5th, 7th, etc. And usually we avoid this kind of operation of the converter, okay, for m greater than 1. If that m becomes very, very large, what we get is basically square wave. Okay, if m is very, very large like this, okay, if m is very, very large, okay, we get what is the output like a square wave. You can understand that there will be no more switching, right? Here, at least in the over-modulation region, there are some switchings here. Okay, in the over-modulation, this is over-modulation output, but in this when the modulation waveform becomes very, very large, right, then it becomes like a square wave operation. Okay, so if it is a square wave operation, we get an output voltage which is shown like this. Okay, m becomes very large, and each switch of the half bridge switches only once in the cycle. Okay, and of course at this point, this is the maximum that you can get out of the half bridge. And how much is that maximum? The maximum that you can get is basically 4 by pi into VD by 2. Okay, this you can do. We have done it previously, that how to analyze the square wave, the fundamental component inside the square wave. We had done it in module A, and that if you can put it their value, and they will come 1.27 times that what is obtained with sine PWM. Okay, so if you get 1 per unit from sine PWM, in square wave operation you will get up to 1.27. You will get 1.27, and in between this 27%, we will talk about it later, up to 1.15 we get this what is known as space vector PWM, or the third harmonic injection, we get up to 1.15. okay, but the problem with the square wave operation, again, square wave operation is generally avoided because we get substantial lower order harmonics. Okay, so usually we avoid square wave mode of operation, okay, in a converter, because it generates this lower order 5th, 7th. As you can understand that for a square wave, the nth harmonic magnitude is 1 by n times the fundamental. So 5th harmonic is generated, third harmonic is generated, so their magnitudes are like 1/5 of the fundamental. Okay, so it's a huge amount of harmonics being generated. So we try to avoid the square wave, and we stick to either sine PWM, or better we go with space vector PWM, which we'll talk about sometime later. But what we see here is that we actually get in square wave up to 1.27 times that which is obtained with the sine PWM. Okay, so if you want to understand a little bit more, you can also refer to my other YouTube NPTEL lecture on high power converters, where I have dealt it a little bit more in details about this. So far we have understood what is the fundamental component, or what is the fundamental output which is obtained at the pole voltages of a half bridge converter. And this expression here, VAOT, you can see here, this is what you get. But so far, and here you can see this is the actual waveform, the blue one, and the fundamental is inside this. But actually, if you do the harmonic analysis, there are actually some high frequency terms here. Okay, there are some high frequency harmonics here which we have neglected so far, and these harmonics are generated because of the switching actions of S1 and S2. Okay, this comes because if you do a harmonic analysis or Fourier transform of this waveform, you will get some fundamental, but you will also get the high frequency harmonics. So let us little bit understand about these harmonics. Okay, so there are actually some elaborate mathematical treatment of that PWM waveform using Bessel functions, which we will not go into. But what is important here is not the magnitude of the harmonic. For our purpose, for example, when we use it in this PWM rectifiers, in that one, what is most important is the position of the harmonics. Okay, not the magnitude of the harmonics. We are not much bothered about the magnitude of harmonics, because we will anyway filter it out with the help of filters. So the magnitude of the harmonics is almost suppressed. So we will take care of that one. But in order to design the filter, the position, okay, the position of harmonics is very important in the harmonic spectrum. So which means that suppose here this is the fundamental, so this is the omega axis and this is the amplitude. Okay, so this is the fundamental, and then you will have harmonics here or here if you do the harmonic analysis. So the position of the harmonics, this is the position of the harmonics, that is important in the harmonic spectrum, whereas magnitude we are not much bothered. We are not much bothered about this one. Okay, so this has less impact. Okay, it has some impact for the how much attenuation of the harmonics we can do, but the position of the harmonics is very, very important. Okay, why? So first we understand where are the harmonics coming. So if Fc is the carrier frequency and F1 is the modulating frequency, with sine PWM, harmonics reside around MF, 2MF, 3MF, where MF is this one. For example, suppose you have Fc as 5 kilohertz, okay, and F1 as 50 hertz. So you will see that your harmonics, the first band will come around 100, the second will come around 200. So this is the first band here, this is coming at 100, so this is the fundamental 50 hertz. The first will come at 5000 or 5 kilohertz, the next will come at 10,000 or 10 kilohertz, like that. MF, 2MF, 3MF, like this. Okay, so this is the place where the main harmonic exists, but there are also sidebands. Sideband means these are the sidebands here. Okay, these are the sideband harmonics. They exist at these places. Okay, so this is a little bit elaborate. Okay, J odd, K even, J even, K odd. This is not important. What is important is where is the first set of harmonics coming. The first set of harmonics come where the Fc by F1, that place. Okay, as I given you, it is the 100th harmonic or 5 kilohertz. So if your carrier frequency is 5 kilohertz, the first band of harmonics will also come at 5 kilohertz. If your carrier frequency increases to 50 kilohertz, your first harmonic will come around 50 kilohertz in a similar way. Okay, so this is important. So this is the position of the harmonics. Now, so for example, suppose you take the harmonics in sinusoidal, so the half bridge one. Okay, in the half bridge VAOT, we have chosen MF equal to 21. Okay, in this case we have taken the carrier frequency to be 21 times 50 hertz. Okay, 50 hertz was the fundamental, so MF is 21. So you can see this, the main harmonic is coming at 21. This is 21. The second will come around 42. The third will come around 63, and so on. But there are also sidebands. Sidebands exist around, say, 17, 19, 23, 25, like this. These are not so important. What is most important is this one, 21. Okay. So this is what is written. Magnitude of the harmonics is not so crucial, but the position in the harmonic spectrum is crucial. Okay, because the filter design is dependent on where is the harmonic. Okay, where is the position of the harmonics. I'll talk about it a little bit later. And one of the things that you can see here is that in full bridge, actually, okay, in full bridge, we can actually cancel the harmonics because there are two legs operating independent of each other. So what happens is, if there is one leg which is producing at MF, the other leg will cancel that harmonics around MF. Okay, so you can see in the previous slide we had this one at 21. Okay, but in a full bridge output, if you analyze this full bridge output, you see that at 21 no harmonics exist, but they have all shifted to the 42nd. Okay, so this is one of the advantages of using full bridge with unipolar PWM. This is unipolar PWM. Okay, and you can always understand that the sine wave is here and it is now closer. The instantaneous error is, so harmonics, why do the harmonics come? Because harmonics is originating because of the instantaneous error between the actual voltage and the PWM voltage. PWM voltage is something which is produced by the converter, but we want to actually produce the sine wave. So the instantaneous error is causing the harmonics. If you reduce the instantaneous error to 0, then there is no harmonics. So in this case, in the unipolar PWM, you can see the instantaneous error has reduced, okay, as compared to a bipolar PWM, right? So therefore the harmonics are improving. In fact, you can see that the harmonics have shifted to 42nd. Okay, so this is what is the important. Now, one thing which I wanted to discuss a little bit is the why is the position of harmonics important. So you see here, I'll take, say, what is the first example. So I'll take two cases. In this is the fundamental, and here are the harmonics. Okay, and in the second case, suppose this is the fundamental, and here are the harmonics. Right? Now, suppose you want to design filters. Okay, so there are two converters. In this converter, suppose this is the 5 kilohertz where harmonics are coming, and this is, say, 20 kilohertz. Okay, you are switching. Now in this case, with the 5 kilohertz, when you 5 kilohertz, remember that suppose you want to design the filter, the gain of the filter, what should it be? The gain of the filter should be 1 here, and then it should fall. In fact, at this point, the gain of the filter should be highly negative. Okay, so let us now try to understand why the position of harmonics is important in when we are talking about this voltage source converters or PWM rectifiers. So now let us see two cases here. So if you see the harmonic spectrum, so first you have this, here is the fundamental, and you have the harmonics coming here, okay, the band of harmonics. So this is corresponding to the switching frequency. Wherever is the switching frequency, the first band of harmonics are coming there. Now suppose we take two examples. Suppose this is 50 hertz, and here suppose in this case this is 5 kilohertz, and in another case you have a converter where the fundamental is here and the harmonics are here, which is, say we take it as 50 kilohertz, okay, 10 times more, right? So now now there are two aspects here, okay. As we why there are two aspects of analyzing why the position of harmonics is important, okay. Now in this case, remember that suppose how does the, say suppose you have a voltage source converter, a PWM rectifier connected to grid. So then you have this PWM rectifier coming here, and then you have a filter, okay. You may have an L filter, or you may have also an LCL filter, but you have a filter, okay. Now what is the function of the filter? The function of the filter is that it tries to remove all these switching frequency harmonics and tries to only allow the fundamental to come at the output, which will interact with the grid, okay. So basically the filter takes out these harmonics. So now you can understand that if we design a filter, right, the filter should have a gain of 1, okay, at the fundamental frequency, because the filter should not attenuate any fundamental component, because that is what we want to get out, and we want to interact with the grid. That is what we will exchange active and reactive power with the grid. But we do not want any switching frequency harmonics to go and interact with the grid, okay. So therefore the filter must be designed such that the gain is 1 up to a certain band of frequencies, and which is called the corner frequency here, and after which the gain should fall. It should fall in such a way that at this in this area, at this position of the harmonics, the gain should be sufficiently low, okay. Now you can see here, now you have to understand that the size of the filter, okay, the size of the filter, L, C, whatever you are using, is inversely proportional to the this corner frequency, okay. So which means that if you increase the corner frequency, this corner frequency here, if you increase it, right, the size of the filter will go down. So therefore clearly we can see that in case 1, okay, this is case 1 and this is case 2, we can clearly see that in case 1 the corner frequency must be what I have shown on the diagram, but if you take case 2, we can actually shift this corner frequency to much more, okay. So now here is the corner frequency, okay. So now in this case you can see, as I told you, the size of the filter is inversely proportional, right. So which means that in this case, in the second case, omega c is more, and so in the second case the size of the filter goes down, Okay, so you have a smaller filter. A smaller filter will take less space, it will have lesser losses, so overall efficiency will improve, right? We want that. Okay, so this is one reason why, as I told you, the position of the harmonics is important. So we will of course prefer to have the harmonics at 50 kilohertz, but on the other hand, the penalty is that if you switch this PWM rectifier at 50 kilohertz, or if you switch at 5 kilohertz, of course the switching losses will be higher in this case. Okay, when you have higher switching, so that means 50 kilohertz, that your switching losses in the converter will be higher. Okay, but on the other hand, your filter size will go down. So this is one way of analyzing the thing. So you can now also understand, going one step ahead, that why do we need actually higher order filters. Okay, so remember that if you have a first order filter, this will go down at -20 dB per decade. On the other hand, if you have a second order filter, then this gain will be like this, and then it will fall much faster. Okay, this will become then -40 dB per decade. Okay, if you have a third order filter, which is not usually used, very difficult to control and stability issues, but if you have a third order filter, then it becomes like this, -60 dB. Okay, so therefore the rapidness, how rapidly the filter gain is falling, is also important. Okay, then if you have a higher order filter, then you can actually increase this corner frequency a little bit more, and then allow the filter to rapidly fall. The gain rapidly falls. Okay, so you get this extra margin of omega c, okay, which will help to slightly reduce the size of your components, right? So that is why we actually go for higher and higher order filters, but then of course there is always a design compromise that we have to make. So this is one aspect of the position of the harmonics. The other aspect of the position of harmonics also comes from the controller point of view. Okay, so what has the controller need to do? Again, I will take one more slide, and let me also draw the controller point of view. So from the controller point of view, suppose you have this as the converter. Okay, so this is the PWM converter here, and in a control system, okay, you generally have a reference. Okay, for example, you are trying to control the grid current, okay, IGD star, and then you have a feedback, and generally you have a compensator. Many of the times we have a PI or some other type of compensator here, or lag lead compensator or something like that. Then you have this PWM converter, and then this gives IGD. Okay, and then we have also a feedback here. Fine, it works like this way. The thing here is that what is the important part here is that when you see the position, so this is the fundamental, and here are the harmonics. Okay, fine. Now note that from the control point of view also, right, the gain of this whole thing, this is called the loop gain. Okay, the loop gain should be high at close to DC. Okay, loop gain should be high close to DC. That means the gain of the control loop should be high close to DC, but very low at switching frequency. Okay, why is it so? Okay, we'll explain. So which means that if you draw the loop gain, it will be something like this. This is the loop gain plot. Okay, loop gain plot. Loop gain means the plant GS. So this is the GS. Okay, and this is the GCS compensator, and this is the HS. Loop gain is GS into GCS into HS. So what does this mean? Okay, let us not go into this mathematics and all. What does this mean? The loop gain should be high, okay, at low frequencies, but in this area, okay, where the switching frequency is here, the loop gain is very small. So which means that so if there is any switching frequency harmonics inside the system, this is the plant is generating the switching frequency harmonics. So those switching frequency harmonics does not excite the whole control loop, okay, because the gain is very small. Okay, so the gain should be very small at the switching frequency, because the whole system should not be excited by the switching frequency. Otherwise, at the output you will get only the switching frequency components getting amplified. You will not be able to control the current. Okay, you have unwanted switching frequency components coming at the output, which you cannot control. Okay, so for example, this IGD often is a step input. Okay, often. So what does the step input mean? Step input has all the frequencies. So which means that if this system has some switching frequency or something like that, and the whole system gets excited because of those high switching frequency components, then we are in deep trouble. Okay, so therefore the control loop is always has a waveform something like this. Okay, of course you will always modify this control loop. It may look like this initially, this pole zero combination, but eventually at the high frequency region, the gain of this control loop, the gain of the control loop should be very small, where the switching frequencies are there. Okay, of course you can have something like pole zero. Here you can modify the bandwidth like that, okay, by placement of the pole zeros from the lag lead compensator or PI compensator. You can make it down or up using the bandwidth here. Okay, this is the bandwidth you can control, but at the switching frequency, you should have a very small loop gain, so that all your switching frequency components go in. You will always play around with the bandwidth. Okay, remember, the bandwidth controls how fast the system is responding. Higher is the bandwidth, faster is your response. So, but remember that the bandwidth, you cannot come close to the switching frequency. Okay, bandwidth means the point, the frequency on the frequency axis, the frequency at which up to which the gain is approximately equal to 1. Precisely like 1 by root 2.7, 70% of the gain equal to 1. So that till that point you should have a sufficiently good bandwidth, okay, because you want this thing to increase. Okay, you want this thing to increase, right, because then your system response will be faster. But you do not want it to go inside the area where switching frequency harmonics are starting to appear. Okay, so this is what I wanted to cover as part of the additional sum material. Now we will talk a little bit about full bridge circuits before going into the three-phase circuit. So when you have a full bridge circuit, basically you have two half bridges working together. Okay, and as I have shown it before, in a half bridge you get Vd by 2 as the fundamental peak voltage. Now of course when you add, so there is one half bridge here and there is another half bridge, left and right half bridges, right? So how much voltage you can obtain from a full bridge? Okay, again you understand that these two half bridges are operating independent of each other. Okay, and so how much is, so the VAB fundamental peak is VAO fundamental minus VBO fundamental. Okay, that will come across the load. Okay, here is A and here is B. Okay, now suppose if these two fundamentals which they are producing is 180-degree phase shifted, the phase B voltage is 180-degree shifted to phase A voltage, then what will happen is we get double the voltage from a full bridge. Okay, so therefore VAB fundamental is VD, where it is double than what we obtained from the half bridge converter. Again, as I told you, leg B can be controlled independent of leg A. Okay, so here you can see one simulation where you see VAO, this is the VAO waveform. Okay, it is getting compared, but VBO, this waveform is getting also compared with the same triangle, but VBO and VAO are 180-degree phase shifted, and therefore this VAB voltage is something like this. Okay, so this is something which is obtained for in the full bridge case. Now we will go into the three-phase condition, three-phase circuit. Now when we have understood, after we have understood, then we can say that basically this half bridge now, okay, this half bridge, this half bridge and this half bridge, these are basically three independent voltage sources. Okay, and we can actually say that these three half bridges can be treated as three AC sources like this. Okay, these are the three AC sources, and how these AC sources behave? These AC sources behave as M times sine omega t, okay, into Vd by 2. These are the magnitudes of the three AC sources. M sine omega t Vd by 2, this will be M sine omega t minus 2 pi by 3 into Vd by 2, and this one will be M sine omega t plus 2 pi by 3 into Vd by 2. Okay, so these are the three AC waveforms being produced at the output of the converter. Okay, and of course they are produced by the help of the three modulating waveforms, right? So we can control the fundamental output voltage of the VSC. So the three modulating waveforms, what are those modulating waveforms? As I shown you, one is the sine omega t, the second one is sine omega t minus 2 pi by 3, and the third one is sine omega t plus 2 pi by 3. This modulating waveforms is between 0 and 1, or maybe minus 1 and plus 1. Okay, and the triangle is between minus 1 and plus 1. Okay, so these three modulating waveforms, what is their property? What are the property? They have the equal amplitude, so this M is usually equal. Okay, M is same, phase shifted by 120 degree. You can see here the phase shift is there. Okay, and has a specific frequency like 50 hertz. So this omega is basically 2 pi into 50. Okay, but you can have other omega also. You can have 100 hertz. Okay, you can also have other phase shift. Okay, it is not necessary that you have a 2 pi by 3 phase shift, right? So these three AC waveforms basically are independent of each other. Okay, the three AC waveform, because the legs, the three half bridges are independently controlled using the three modulating waveforms, right? So it is not necessary for this to be balanced, right? So you can actually have this waveform as M1 having an amplitude M1, this waveform M2, and this waveform M3. Okay, because you are going to switch accordingly these switches. Okay, the three half bridges you can switch as M1, M2 and M3, right? And that is the way the three, so therefore the modulating waveforms for the three half bridges need not be balanced. Okay, this is important. You can have an unbalanced operation of the voltage source converter. Okay, so basically what therefore we understand is that we do not necessarily have to, when we analyze the the voltage source converter, we do not necessarily think about these things. We do not think about all these things, right? It is not necessary for us to think that, okay, there are two switches, three half bridges. We do not work like that. Rather, so we take this VSC as a box, and suppose we are connecting to the grid, Okay, so this is the grid, and there is a filter, and there is a VSC. We have connected a grid connected VSC. This can act as a PWM rectifier. So here this VSC here, okay, we think it like this thing here. Okay, the VSC is basically a controllable voltage source. Okay, and it is this VAN, VBN, VCN, which can be balanced or unbalanced. Okay, but basically this VAN, VBN, VCN is in my hand. Okay, as a designer or as an user, I can change. So this AC source is nothing but m sine omega t into Vd by 2. Okay, this is the AC source given by this mathematical expression m sine omega t into Vd by 2, which I am going to inject into this circuit. Okay, similarly this one is m sine omega t minus 2 pi by 3 into Vd by 2, and similarly this one sine 2 pi omega t plus 2 pi. So basically, as you can see here, this VSC is nothing but a 3-phase controllable voltage source. Okay, it is fully controllable. Okay, so the grid connected VSC with an L filter is shown here, which we will use several times, and a motor can. So for example, this can also be a motor. For example, this can be a PMSM. Okay, right? So in this case, this one will become the E. Okay, which is the E is the excitation EMF. Okay, and this is the resistance of the stator. Okay, resistance, and this can be like the synchronous reactance. Okay, synchronous reactance X, which we see in a synchronous machine, right? So therefore, if you understand the operation of a voltage source converter with a grid connected application, you can also apply the same principle for a motor drive application. Okay, like a PMSM or even induction motor also. Slightly changes. Induction motor has this excitation EMF thing will change, but the basic principle will remain the same. So now what is interesting to observe here is that therefore this circuit becomes a very standard circuit. Okay, why it is a standard circuit? Because now we have a situation where we have this AC source, this RL, and then there is another AC source. Okay, so two AC sources and with a Z in between. Okay, so V1 and V2. Okay, this is something which we know very well. Okay, and we know that, okay, suppose this Z is nothing but X. Okay, the R is very small, so R is very, very small. Okay, we neglect the contribution of R, then Z is almost equal to X. Therefore, then we know that, okay, the power is nothing but V1 V2 by X into sine delta, right? And so you can control the power flow, right? This we have seen with like a synchronous machine connected to infinite bus bar, right? So there also we have the one E, the excitation EMF, the synchronous reactance, and the grid voltage. So then this equation comes repeatedly. Okay, V1 V2 by X into sine delta is the power which is getting. So basically this is basically the two AC sources exchanging energy between them, and clearly this is bidirectional in nature. Okay, absolutely, this is a bidirectional converter. Okay, so the energy actually can flow from the grid to the VSC. Okay, so the energy can flow. So the energy can flow both ways. Okay, it can flow from the grid into the VSC or from the VSC to the grid. Okay, so the energy flow is bidirectional. In fact, that is why it is, as I told you at the start, okay, it is not necessary to talk about this as a rectifier or an inverter. Okay, rectifier and inverter, it is not needed to, we can just take, we can just use the word converter here, because as I can understand, the energy can easily exchanged from the grid energy, because if you say delta in this previous equation, if you change the value of delta, delta is the phase angle between V1 and V2. If you make delta negative, the energy may flow one direction, and when you make the delta positive, the energy will flow in the other direction, right? So therefore it is possible for us to control the energy flow, and so this is a very useful tool in our hand. So the voltage source converter in power electronics is a very useful AC AC converter in our hand, which we can easily, with the help of this kind of modulating waveforms, 3 modulating waveforms, we can easily actually control that converter to exchange energy as and when required. Okay, so this is how the whole converter behaves. Now there is something else which I wanted to highlight here, is that although this is the pole voltage, we have so far said that okay, here this thing can be represented by a pole voltage. Okay, so this is the pole voltage, right, and this is the VAO equal to m sine omega t into Vd by 2. Okay, that is what we said, that this pole voltage is coming here. Okay, this is the pole voltage, so I will replace this one with this pole voltage here. Okay, and then there is another pole voltage here, and then there is another pole voltage here, and then I will not look into this circuit anymore. I do not need to look into this circuit anymore, and then I will start looking from this circuit downwards. There may be instance like yeah, so there may be a grid here also, right? So this is how we look into the whole thing, right? So let me just rub it this one because otherwise this will be clumsy. Okay, so yeah, now one of the things that is important is, although I have talked about the pole voltage here, okay, the pole voltage comes here, but the pole voltage is here, this is the pole voltage, but what is this voltage? This is the load phase voltage. Okay, it is important to know what is actually coming across the VAN. Remember, we had generated the pole voltage here. This was the A point. The pole voltage is between these 2 points. Okay, VAO voltage, that is the pole voltage, and we are now trying to find out what is this load phase voltage. Okay, how much is it coming to the load voltage? Let me give you the answer first. The fundamental component of the pole voltage and the fundamental, whatever is the fundamental inside the pole voltage, the same fundamental comes onto the load phase voltage. Okay, so there is no loss there. Okay, so fundamental component in pole voltage, we'll show it in pole voltage is equal to fundamental component in load phase voltage. Is the same. Okay, the same content is there. Okay, so how can you know that? So in order to know that, we will see what is the load phase voltage. So VAN, this voltage is nothing but VAO plus VON. Okay, this you can do mathematically, right? VAN is equal to, yeah, so you, because VA minus VO plus VO minus VN, right? This you can do, and therefore you can write it like this way. Okay, so this will go to VAO here, right? So similarly you can write VBN and VCN here. Now in this case, because it is a star connected load, okay, so therefore the sum of the 3 currents must be equal to 0. So therefore VAN plus VBN plus VCN by Z equal to 0. So when you substitute this back into this equation, we see that VON is this voltage, which means, this is important, which means that if you see here, there is an instantaneous voltage always present, okay, between these 2 points. Okay, VON, this is an instantaneous quantity. These are all instantaneous quantities. So VAO plus VBO plus VCO divided by 3. So which means therefore that you cannot actually short this point to this point. This is not possible. This is absolutely prohibited. Okay, this you cannot do because there is always an instantaneous difference of voltage between the load neutral point and the negative of the DC link. Okay, so if you connect it, then a huge current will flow, and you cannot do that. And the magnitude of this instantaneous voltage is given by this quantity. Okay, and so if we can substitute here, VAN, VBN and VCN will come out to be like this: 2/3 VAO minus 1/3 VBO and 1/3 VCO. Okay, so this is the load phase voltage, whereas this VAO, VBO and VCO, these are the pole voltages. Okay, so this is the relationship. So load phase voltage and the pole voltages have a relationship. So these are the pole voltages here, and they have a relationship between them. Okay, 2/3 VAO minus 1/3 VBO and minus 1/3 VCO. So yeah, so therefore you can actually so this is one simulation waveform to show you that okay, how is this VAO, VBO and VCO look like. As you can see, the 3 modulating waveforms are shown here, right? And VAO, so what I have done is this sine triangle comparison, and VAO, this voltage comes by comparing the modulating wave with the triangular wave. VBO comes from this waveform, and VCO comes from this waveform. Okay, and so the actual waveforms, this is what is important, the actual waveforms, this is the PWM waveforms. Okay, so this sine wave here is embedded inside. So the sine wave, this sine wave, the fundamental component is embedded inside. This is the fundamental which is embedded. When I do a Fourier transform, then I get that fundamental output, and here is the actual line voltage output. Now we will take an example. We actually if you take this one and we see that VAN, VBN and VCN, these are the load phase voltages, and this was the pole voltages. If you see this one, okay, we have to prove that the we will see that the VAN, the fundamental component in VAN and the fundamental component in VAO are the same. Okay, so how can we see that? So suppose VAO, we see that this is the voltage. Okay, this is what we had already found out, okay, in the few slides back, Vd by 2 into 1 plus m sine omega t, and therefore VBO is also like this and VCO is like this. Okay, Vd by 2 into 1 plus m sine omega t. So therefore when you have this one, okay, you put it into that formula of VAN, 2/3 VAO minus 1/3 VBO minus 1/3 VCO, right? And when you put this, then you see m sine omega t into Vd by 2. Okay, and that is same as this water. So therefore the same fundamental, so VAO had this fundamental, okay, m sine omega t into Vd by 2. You can see here VAO had this m sine omega t into Vd by 2. This was there inside the voltage here. That same voltage is also there inside VAN. So the fundamental quantity, fundamental voltage across the load is same as the fundamental pole voltage from the 3-phase converter. So if we know what is the fundamental quantity in the pole voltage, we will also know what is the fundamental quantity in the load voltage. So we don't have to do double calculation. But there is always an instantaneous voltage difference between the load neutral and the negative terminal. Okay, so we cannot short it. Okay, here you can see here that one of the things that you can observe is that this Vd by 2 is common to all the 3 phases. Okay, this Vd by 2 is actually called the common mode voltage, okay, of the output of the converter. Okay, there can be other values of common mode also, you'll see in the space vector PWM, but Vd by 2 is common for all of them. That is why the Vd by 2 do not come in the line voltage, and it will also get cancelled in the load phase voltage. In that, if you see here, no Vd by 2, no DC quantity. Okay, the pole voltage had this DC inside of this VD by 2, but the load phase voltage does not have this DC quantity anymore. Now let us see and compare the load voltage magnitudes, okay, what we have discussed so far. And you can see here in a half bridge, the peak pole voltage is MVD by 2, okay, and so the RMS load voltage is MVD by 2 root 2, right? RMS is 1 by root 2 of what you obtain as the peak. In full bridge, of course, you get double than what you get in a half bridge. So in a full bridge, the output peak voltage is M times VD. M is the modulation index, and the RMS voltage will be MVD by root 2, which is 0.7 VD, right? So this is what you can get with M equal to 1, okay? So this is M equal to 1, fine. And the last one is the three phase, okay? The peak pole voltage is MVD by 2, okay, and the RMS load voltage, okay, the load phase voltage, I should say, is the same, right? MVD by 2 and divided by or into 1 by root 2, okay, 0.35 VD when M equal to 1, and it is obtained at per phase, okay. Of course, the RMS line voltage will be root 3 times what we had obtained earlier and will be equal to 0.6 VD if M equal to 1, okay. So this gives you some idea of how much line voltage you can obtain, RMS value of line voltage given a certain value of DC bus voltage when you use sine triangle PWM, okay. But note that this voltage can be increased, this voltage magnitude can be increased by another 50% by the addition of common mode voltage, or like 15 by space vector PWM or some technique like that, or third harmonic addition. We can increase by 15% more, okay. And so that is the maximum that you can get out of this converter in linear modulation, okay. So let us take an example of a very quick example. A three-phase voltage source converter has input DC link VD equal to 700 volt. The converter is operated using sinusoidal PWM with M equal to 0.9 and 50 Hz fundamental frequency. The three-phase active and reactive powers are load given by this one and this one. The first question is, what is the RMS value of fundamental pole voltage, VAO RMS? How will I find out? So VAO voltage, right, is the what is the expression? The expression is M into VD by 2, okay, that is the peak voltage, okay, and therefore the RMS voltage is this much, right? So in this case the value of M is 0.9 and the DC bus voltage is 700, so this is 350 into 1 by root 2, and this value will come out to be 223 volt, okay. So this is the fundamental pole voltage VAO RMS, okay. The second question is, what is the RMS value of fundamental load voltage? Of course, the fundamental pole voltage and the fundamental load voltage, they have the same magnitudes, right? So this should be the same here. There is no loss, because there is no place to lose the voltage actually. So 223 volt, the same fundamental will come in the load voltage also. Now, what is the per phase value of load resistance and load inductance? In this you have to do some calculation, which I am not doing here. Basically, once you know the fundamental load voltage, you can know, like, this is VAO by Z is the VAN, this is the load phase voltage, by Z is the IAN. So this is what is the current, right? And Z equal to R plus JX, okay. Which we have to find out. So once you get this one, then the S which is flowing through it is the total S of the three-phase converter is 3 times VAN into IAN star. Okay, and when you do this calculation, then you will get some active power and some reactive power. Okay, and that you have to compute, that you have to equate with 18 kilowatt and 6 kVAr. And this is easy to do, and the answers are given here, and you can verify it yourself. Okay, now the last part of the question is, if the fundamental line-to-line voltage needed from this converter is 400 volt RMS, what is the DC link voltage required, assuming sinusoidal PWM with modulation 0.95? So if the line voltage, now you are talking about fundamental line-to-line voltage is 400 volt RMS. So how much is the fundamental line-to-line voltage from this converter? So the pole voltage is M into VD by the pole voltage is M into VD by 2. That's the peak pole voltage, and the RMS voltage is this much. What is the line voltage? Line voltage is this much. Okay, so this is the fundamental line voltage RMS value. Okay, and this value should be equal to 400. Okay, where M is to be 0.95, right? So therefore this will be 0.95. And now you find out what is the value of VD. So the value of VD will come out to be 687 volt. Okay, so this is the answer here, 687 volt. Okay, so with this we actually have started working or understanding how the voltage source converter works. And in the next subsequent classes, we will start working on or understanding on the steady state operation and the phasor diagrams, etc. Thank you.